Alright guys, today we're going to be learning a lot, so buckle up. First thing we're going to talk about is we're going to talk about the coordinate plane. Now you guys have seen this coordinate plane before. It's nothing new. We're just going to go over the basic information about it. So first of all, the x-axis and the y-axis. There are two axes on this coordinate plane. I'm going to highlight one red, and I'm going to highlight the other one blue. Now, these axes split the coordinate grid or coordinate plane into 4 equal sections, and the red one here is what we call the x-axis. It's a horizontal axis, and the blue one here is what we call the y-axis. It's the vertical axis. So what we're going to do is we're going to label these just so we know. So on the x-axis right here, we're going to go all the way to the end on the right side, and I'm going to put a lowercase cursive x because we label lines with lowercase cursive letters, which we'll talk about later on in the year, but we're going to call this the x-axis. Now this one's the y-axis, so I want to label it with a y. I'm going to go to the very top of it, and I'm going to label it with a lowercase cursive y. Now, a coordinate plane is all about ordered pairs and where they can be located at. A coordinate on the plane is always written in the order of x comma y. Now notice how the x comes before the y. This is always in alphabetical order. That's why it's called an ordered pair. So if I wanted to find a coordinate on this graph, it would be right here. Let's say we have one right here, and I'm going to call this, well, come on. I'm going to call this point A. And if I wanted to know what is the ordered pair, what is the coordinate of this point, I wouldn't actually at this point be able to tell you. And the reason that I wouldn't be able to tell you yet is because I don't know what the scale is. Now the scale on any coordinate plane is the most important part. Now for instance, you know that this is 1, 2, 3, 4 squares to the right, but we don't know that that's actually 4 because we don't have a scale to tell us what they're counting by. So before we can give the ordered pair for this point, let's give a scale for the x-axis and the y-axis. Now, it does not matter what the scale is. If I wanted to count by 5s, I could. If I wanted to count by hundreds, I could. But for simplicity's sake, I'm just going to count by 1s. So that means this would be 1, this would be 2, 3, 4, 5, 6, 7. And whatever you count by going to the right, you have to count by that going to the left as well, because this is all one number line. So that means this would be 0, and then we'd have -1, -2, -3, -4, well, if my pen would write, -5, -6, and -7. So whatever you count by going to the right, you have to count the same going to the left. Now that does not mean you have to have the exact same scale for the y-axis. If you wanted to, you could have a scale of 1 on the x-axis and a scale of 100 on the y-axis. Or you could have a scale of 1 on the x-axis and a scale of 20 on the y-axis. It doesn't matter. But again, for simplicity's sake, let's just use a scale of 1s. So 1, 2, 3, 4, 5, 6, 7, and then whatever you use going up, you have to keep it the same going down. -1, -2, -3, well, -4, -5, -6, -7. Now that you have a scale, you will be able to write the ordered pair for point A over here. Now again, the ordered pair must be in alphabetical order. So the x has to be first, the y has to be second. So if I look at this point right here, the x value that it's located at, it's located right at the x value of 4. And the y value that it's located at comes second, it's located at 5. Now, here's what's really important about an ordered pair. Not only do you have to have them separated by a comma, so we know that they're two separate numbers, but it is written with parentheses around it. So you have to have an ordered pair with parentheses around it. Just be aware, quizzes, tests, everything in the future, if you don't have parentheses around your ordered pair, I take off points. Now, the most important ordered pair on the coordinate plane is actually the one right at the middle, at the intersection of the two axes, this dude right here. And that ordered pair has a coordinate of 0, 0. It's at 0x, 0y. It's right where the two axes intersect. It marks the center of any coordinate plane. Now, this ordered pair has a very special name, and it is called the origin. The origin is always at 0, 0. Now finally, there's one more thing that I want to talk to you about coordinate planes, and that is a quadrant. Now a quadrant is one of 4 separations of the coordinate plane. So since we have two axes, the x and the y, they split my coordinate plane into 4 different parts. Those are each called quadrants, and they all have their own special number, and we label quadrants with Roman numerals. Now we're going to have a quadrant 1, quadrant 2, quadrant 3, quadrant 4, but to remember which one's which, quadrant 1 will always be the positives that are together. So we work with the positives and the positives a lot, so this is going to be quadrant 1. So if you want, you can label them up here. I'm going to label them big so you guys can see that this is quadrant 1, and notice it's a Roman numeral that I've made there. Then we go counterclockwise. It's a little bit weird. So quadrant 2 is 1 to the left. This is quadrant 2. 1 down is quadrant 3. And then 1 to the right is quadrant 4. And quadrant 4 is the IV. Okay? So we label those with Roman numerals. Quadrant 1, 2, 3, and 4. All right, now that we've talked about what a coordinate plane is, let's talk about something called a relation. Now, a relation is a set of ordered pairs. I'm going to highlight that so you guys can see it. A relation is a set of ordered pairs. Now remember, a set includes the set brackets, which were the fancy brackets, okay? Now, a set of ordered pairs is a relation. We can represent a relation either by writing just the set of ordered pairs, so like with the fancy brackets and all of that. We can represent it as a table, we can represent it as a graph, or we can represent it as a mapping. Now, let's talk, we have an example right here. Let's talk about what this really means. So it says, express the relation right here as a table, a graph, and a mapping. So they've given us a relation. They've given us a set of ordered pairs, which you can tell right here because it's got set brackets. And they just want us to show how a relation could be written in a table, could be graphed on a graph, or could be mapped. So what we're going to do is we're going to start with the table. Now before we start with the table, this is going to seem a little weird. In my relation, I have 3 different ordered pairs. I want to label these ordered pairs because we're going to talk about them a little more later. So I have 3 ordered pairs. I'm going to label them each with a capital letter, and let's not make it complicated, please. Let's just start with capital A. So my first ordered pair is going to be capital A. My second ordered pair would be capital B. And my third ordered pair would be capital C. Okay? If we had a fourth ordered pair, we'd call it capital D. If we had a fifth one, we'd call it capital E, so on and so forth. Don't make it complicated. So we have a relation of, so a set of ordered pairs. Let's start by expressing it as a table. So I want to take each of these ordered pairs and split them up to make a table. So let's start with ordered pair A. I want to take the x value, which remember, ordered pairs are written x, comma, y. So the x value, goodness, is the first number. And I want to put that first in the x column. Now, if the x value is 1, it's also paired with this 1 here. So that means the y value would be 1. Now we can go on to point B. Point B has an x value of 0 and a y value of 2. And point C has an x value of 3 and a y value of -2. So we have taken that relation, the set of ordered pairs, and we've just transferred it to a table. It's still the same relation, it just looks a little bit different. Next, they want us to express the relation as a graph. Now they've given us a graph, they've identified the x and the y-axis, which is good, but before you can graph, and this is very, very important, we need to have a scale. Now, I don't care what the scale is. You need to make sure it fits, though. So if you look, the biggest x value that I have to get to is 3, so I have to get to at least 3 on this x-axis. And the biggest y value that I have to get to is 2, so I have to get to at least 2 on the y-axis. So let's not be complicated about this. It looks like a scale of 1 will be just fine, so let's go with a scale of 1. That means this guy would be 1, this would be 2, 3, 4, 5, 6. And then this would be -1, -2, -3, -4, -5. And we can count up 1, 2, 3, 4, and down -1, -2, -3, -4. Now that we have a scale, we can take these 3 ordered pairs and plot them on our graph. So my first ordered pair, point A, is at 1, 1. So it is in alphabetical order, x, comma, y. So that means on the x-axis, first I need to find 1, and then on the y-axis I find 1. So we can put a point there. And this is the most important part. Here's why we labeled it. I need to know that this represents this ordered pair. So we can't just put a point and call it good. We have to label that point. Since I labeled it with a capital A, now we need to put a capital A next to it. That's saying, hey, this is the ordered pair that represents this point right here. Okay? Now point B, 0, 2. So that's 0 on the x-axis. So here's the x-axis, here's 0. And then 2 on the y-axis, this guy right here. Put a point, label it B. And then point C, 3, -2. So 3 on the x-axis, -2 on the y-axis. Put a point, call it C. So I've taken the relation and I've expressed it as a table and a graph. All that's left is the mapping. Now the mapping is just a little bit different. You guys have not seen this yet. A mapping illustrates how each element of the domain is paired with an element of the range. So at this point, you guys haven't really talked about domain and range, so let's define what they mean. The domain is just the set of x-coordinates of an ordered pair. The domain is a fancy word for all of the x-coordinates that I'm working with. That means the range is the set of y-coordinates of the ordered pairs. So if you look at the ordered pairs that they gave us at the very beginning, all of the x-coordinates, 1, 0, and 3, are the domain. The y-coordinates are your range. So if I look at my table, it made it a little easier to see. The x values are my domain, the y values are my range. So what we're going to do is we're going to take these ordered pairs and we're going to split it into the domain and range, and then we're going to map one onto the other. So when you put your domain values into your mapping and your range values into the mapping, it does not matter how you put them. I personally like to put them in numerical order. It helps me keep track of what I have. You do not have to do this. So for my domain, my x values are 1, 0, and 3. I need to take all 3 of these and just put them in this circle. So I like to put them in numerical order. You don't have to. You can put them just like this if you would like to. Now the range values are just my y values. So 1, 2, -2. Again, I like to put them in numerical order. You don't have to. -2, 1, 2. Now at this point, we have split the domain and range, but that's not what a mapping is. A mapping illustrates how each element of the domain is paired with an element in the range. So we have to show what they're paired with. We have to map the domain onto the range. So here's how we do that. First of all, the domain with the x value of 0. We need to see what 0 was paired with. Well, according to the relation that they gave me, 0 is paired with 2. So I need to draw an arrow from 0 to 2. And it looks like this. Notice the arrow goes from left to right. The arrow goes from the domain to the range. It does not have arrows on both ends. We do not go from the range to the domain. We go from the domain to the range. Now, let's look at the next value, 1. What y value was my x value of 1 paired with? It was paired with a y value of 1. So 1 maps to 1, from left to right. And then finally, my domain value of 3 was paired with a range value of -2. So I draw an arrow from 3 to -2. That is a mapping. So here I've taken a relation, which is a set of ordered pairs, and I have expressed it as a table, a graph, and a mapping. Now on number 2, let's try it again. So it says express the relation of -2, -1, 3, 3, and 4, 3 as a table, a graph, and a mapping. So the first thing, this is a relation. It's a set of ordered pairs. We need to identify it as A, B, and C. Capital letters. And we need to transfer these values onto the table. So my first ordered pair is -2, -1. So the x value is -2, the y value is -1. B is 3, 3. The x value is 3, the y value is 3. C is 4, 3. X value is 4, y value is 3. So we've taken my relation, we've expressed it as a table, now onto the graph. Most important thing of a graph is the scale. Now, I understand these are kind of small graphs and hard to see, so watch what I do. I want a scale of 1. I know that's going to be plenty. So if I had a scale of 1, this would be 1, 2, 3, 4, 5, 6. I'm going to go all the way to the end, and since the very end line would be 6, I'm going to put a 6 out here. That way I'm smart enough to realize, okay, there's 6 lines, it goes all the way to 6, that must be a scale of 1. So if I go this way, 1, 2, 3, 4, -5, so this is -5. Then if I go up, 1, 2, 3, this is 4, and down, -1, -2, -3, -4. If you would like to label each and every line, that's totally okay, but I just find this a little bit easier to look at, a little bit easier to read. So now I can take my relation and plot the ordered pairs on the grid. So I have -2, -1. That's an x value of -2 and a y value of -1. Put a point, label it capital A. If you do not label your point, you miss a point. Then my point B, x value of 3, y value of 3. Well, if it would make a, label it capital B. And then 4, 3. So I need to move that B. I'll put that B over here. 4, 3. So x value of 4, y value of 3. Put a point, label it C. So we've taken our relation and expressed it as a graph. Finally, we need to take our relation and express it as a mapping. Now remember, domain is your x values, range is your y values. So my x values are -2, 3, and 4. And my y values are -1, 3, and 3. However, since we have the number 3 twice in my y values, there's no need to write it twice. So what my what my range really is just -1 and 3. 3 is used twice, but we don't need to write it twice. If you write it twice, you're technically wrong. Now let's draw the mapping. So on my domain, -2 was paired with -1. So I'm going to draw an arrow from left to right, from -2 to -1. My domain value of 3 is paired with 3, so I draw an arrow from 3 to 3. And my domain of 4 is paired with my range of 3, 4 to 3. Notice how this 3 has 2 arrows to it, and that's okay. You do not write the number twice. We don't repeat ourselves. So, a relation. is just a set of ordered pairs, and we can express it as the actual set of ordered pairs, a table, a graph, and a mapping. Now we're going to talk about special things called functions. A relation is a function when every element in the domain maps to exactly one element in the range. So a function is a special kind of relation. So remember, a relation was a set of ordered pairs. For a relation to be a function, every element in the domain maps to exactly one element in the range. So on 3, 4, 5, all the way through 8, it says, determine if the following relations are functions and explain. So every element in the domain needs to map to exactly one element in the range. So on number 3, my domain, -2, 3, 5, 11, needs to map to exactly one element in the range. So let's see if that happens. -2 maps to 1. So -2 maps to exactly one element over here in the range. 3 maps to 14. So 3 maps to exactly one element in the range, no more, no less. 5 maps to 6. Again, it only maps to one number in the range. And 11 only maps to 8. So every single element in my domain is mapping onto exactly one element in the range. If it's mapping onto 2, then that's wrong. If it's mapping onto none of them, then that's not a function. So this, number 3, is a function. So we need to start by writing function. However, there's this tricky word right here, and that says explain, which means we need to go a little bit more into detail. And we know it's a function because every element in the domain maps to exactly one element in the range. So we need to write that. This is a function because every element in the domain maps to exactly one element in the range. If you need to pause the video and write that down, please do so. Now let's look at number 4. On my domain, let's start with -7. -7 maps to -3. That's exactly one element in my range, so we're okay. Now if I look at 0, 0 is mapped onto 6, and 0 is mapped onto 9. If you'll notice, 0 in the domain is paired with more than one element in the range. So that can't happen because since 0 is paired with 6, 0 can't already be paired with 9. That would be like me partnering up Susie with Jack and then saying Susie needs to be with Amber. That can't happen because I already paired Susie with Jack. So this number 4 is not a function because the element 0 in the domain maps to more than one element in the range. Number 5, if I start with 1, 1 in the domain maps to -3. So 1 is mapped to exactly one element in the range. 2 in the domain is mapped on to -3. So even though 2 is mapped onto the same number that 1 is, it's still only mapped to exactly one element. So we're still okay. 3 is mapped on to exactly one element in the range. And 4 is mapped on to exactly one element in the range. So number 5 is a function because every element in the domain is mapped to exactly one element in the range. Yes, it is the same element in the range, but that's okay. What's not okay is if you have one domain mapped to more than one element in the range. So here's kind of a little trick that helps visually. If you have in your domain one arrow coming off each number, you're okay. If you have in the domain 2 arrows or more coming off of one number, it's not a function. Now number 6, they still want us to determine if it's a function, but instead of giving us a mapping, they're giving us a table. Well, that's not a big deal because we understand that a table and a mapping are just different ways of expressing relations. So if you wanted, you could sit here and you could make a mapping to get a visual of it, but let's just take a look. So on number 6, they're pairing the x value of 2 with the y value of 3. Now remember, x values were domain, y values were range. So 2 is paired with 3. 4 is paired with 5. 6 is paired with 7. And 8 is paired with 9. So what I want to make sure, first of all, is that every single element of my domain is different. 2, 4, 6, 8. I don't have any of those numbers repeating. And all of them are paired with exactly one number. So number 6 is a function because every element of the domain maps to exactly one element in the range. And again, if I wanted to draw that out, if I wanted to map that out, 2, 4, 6, 8, 3, 5, 7, 9. 2 goes to 3, 4 goes to 5, 6 goes to 7, 8 goes to 9. That definitely is a function. On number 7, again, I'm only going to look at the x values for a second, the domain values. -8, 3, 7, 19. Those are all different values. Notice they're all paired with the y value, which is good, but since these are all different, this is a function because an x value was not paired with more than one y value. So again, our explanation, every element in the domain maps to exactly one element in the range. Number 8, I'm going to look at my domain, so my x values, and I have 5, 7, 5, 3. Now if you'll notice, I have 2 5s. Now right away that doesn't necessarily mean it's not a function, we just have to check one thing first. Here we paired 5 with 2, and then here we paired 5 with 0. Now if there was a typo or something and they said 5 was paired with 2 and 5 was paired with 2, we'd be okay. But since those are different numbers that they are paired to, this 5 repeats itself, number 8 is not a function because the element 5 in the domain maps to more than one element in the range. Now we want to determine if a graph is a function. So we know how to determine if a mapping is a function, if a table is a function. Now to determine if a graph is a function, we need to use something special called the vertical line test. Now the vertical line test is pretty much exactly what it sounds like. We're going to use something special called vertical lines to determine if each graph is a function or not. Now here's what we need to do. You need a straight edge, and we're going to see if we can draw vertical lines through any part of the graph that they give us. And if it only goes through one point when we draw it, it's a function. So for example, on this first one, I'm going to draw a vertical line right here. Notice when I draw that vertical line, it goes straight up and down, has arrows on the outsides of them. It only intersects my graph in one place. That's good. Now, let's see if I draw a vertical line somewhere else. What if I draw a vertical line right here? Again, it only crosses the graph in one place, which is great. I want to know if I choose any point on this line, will it always only go through one point? So I'm going to try and choose the trickiest part of this graph, which to me might be like in the middle or on the ends. So if I draw a vertical line right in the middle, again, it only crosses my graph in one place. So since I have drawn vertical lines and it's only crossing my graph in one place, this is a function. And my reason being is because it passes the vertical line test, which we can abbreviate as VLT. Okay? Now, to prove that it is a function using the vertical line test, I require at least 3 vertical lines drawn to show that it crosses in one spot each time. So again, to use the vertical line test and to prove that it's a function, you have to draw at least 3 vertical lines. Now let's go to the second one. The second one we have is a circle. I just want to see if it's a function. Now we know it's a graph because they graphed it, but that doesn't always mean it's a function. To prove that it's a function, I need to draw a vertical line through any part of the graph, and it can only cross the graph in one location. So let's say I just choose right here. Right away, I hope that you notice it intersects my graph once, twice. So since I drew that one vertical line and it crossed my graph twice, this is not a function. Reason being, because it fails the vertical line test. Okay, and you only need one vertical line to prove this is false. On the third one, I've got kind of like a curvy guy going on here. If I draw a vertical line through this point, we cross in one place, so we're okay so far. Next, what I want to do is I kind of want to look at the places where it would be a little tricky, like maybe questionable. If I were to draw it like kind of where the arrow goes, so we're aware when your graph has arrows, it's telling you that it's going to continue on in the same manner that it has been. Like it's not going to change anywhere up here. So if I were to draw a vertical line right where I think that arrow is, we can still see it only crosses the graph in one place. I know that it kind of looks a little weird because it looks like it might go on straight. What's happening is this is curving and curving and curving, and it's still curving and curving and curving. It's still going to do the same thing. So yes, that only crosses the graph in one place. And what if I try over here? Again, that graph, remember, goes out and out and out, so it only crosses the graph in one place. This is a function because it passes. Whoa, if I could spell the vertical line test. Okay, the next one, kind of interesting. They gave us a vertical line. So when I draw a vertical line through my graph, it has to go through the actual graph that they gave you. I can't draw a vertical line over here and say, oh, look, it works, blah, 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 because that's not going through the graph that they gave me. You have to draw a vertical line through the graph that they gave you. And in doing that, on this fourth one, you'll notice that really we definitely go through more than one point. I am lining up right on top of this vertical line, which means that I'm crossing the line here and here and here and here and here. There is an infinite amount of times that I'm crossing the graph. So a vertical line actually is not a function because it fails the vertical line test. Now let's go through this guy over here. Notice this guy is less of a line that they graphed, it's more of points. So you can only draw vertical lines through where they graphed. So like if I drew a vertical line here, notice it doesn't go through any of the points, so it doesn't go through the graph. You can only draw vertical lines through where they graph. So if I draw one here, through that point, it only goes through one point, that's good. If I draw one here, it only goes through the points that they have on the origin, so we're okay. If I draw one here, it only goes through one point, so we're still okay. So this graph is a function because it passes the vertical line test. So again, that means that on my red one, my blue one, and my other red one, these middle three, those are functions. Every element in the domain maps to exactly one element in the range. This green one and purple one are not functions because they failed the vertical line test. That means some element in my domain maps to more than one element in the range. Finally, what I want to talk about is 14 through 17. Now, they're saying now there's a special kind of notation for functions. And this is an equation right here in function notation. Now, we have seen equations before. You guys have worked with it in the past. It's usually like y equals x minus 3 or x plus 7 or something along those lines. This is almost the exact same as that. However, instead of a y value, we have this dude right here, which we read as f of x. When it's written like this, it means, yes, it can give us a graph, but the main difference is that when we have this f of x instead of the y, they're telling us this has to be a function. They're telling us that every element in the domain of this guy has to map to exactly one element in the range. So it's kind of awesome because when they give it to us, we know without a doubt this is a function. We don't have to worry about checking or doing any tests. It's definitely a function. Now, on 14 through 17, it tells us if f of x equals 2x minus 4, so this is a function. This is a relation that has every element in the domain mapping to exactly one element in the range. And g of x, so it doesn't matter if it's an f or a g or an a or a b, as long as it's followed by that parentheses x equals x squared minus 4x, is also a function. They want us to find each value. So in 14, they want us to find f of 4. Now I know that looks like f times 4, but function notation is a little bit different. We're going to take one of these two equations and we're going to substitute some things in. So you have to be smart about which equation to use. Notice how they're working with the one that starts with an f, so that means this guy is actually going to be working with this guy. So if f of x equals 2x minus 4, I want you to go ahead and write that down here because that means that's what one we're going to use. They want us to find f of 4. Now, here's what this means. If you'll notice, the only thing that's different from here to here is they took out that x and put in a 4. So that means with this guy here, everywhere I see an x, I'm going to replace it with a 4 and see what I get. So f of 4 equals, and this is really important, wherever you substitute in a number, you need to put parentheses around it. So here, I have 2 times x minus 4. Since I'm putting in a 4 for x, wherever I see an x, I need to put parentheses around it before I put in that 4. So instead of 2x minus 4, I'll have 2 times 4 minus 4. Now, I just need to simplify this side over here. So f of 4 stays the same. We bring it down. And you can do this in your head. You can do it in your calculator. You can write it down if you need to. For me, I know that 2 times 4 is 8, and 8 minus 4 is 4. So f of 4 actually equals 4. Box your answer. You have to have that function notation there. So number 15. We have g of 2. Notice this starts with a g, so that means we're going to use this equation right here. Let's go ahead and take this equation and write it down here. G of x equals x squared minus 4x. Notice that instead of g of x, we have a 2. So that means everywhere I see an x, I'm going to want to put a 2. So I'm going to go through and put parentheses everywhere I see an x. Notice I didn't put parentheses around x squared, just the x, and not the 4x, just the x. Now let's go through and substitute 2 in everywhere we see it. So g of 2 equals 2 squared minus 4 times 2. You need to put parentheses around it every time you see it. Now we can go through and simplify. So bring down your g of 2. I know that 2 squared is 4, minus 4 times 2 is 8. Well, now I can simplify that. Bring down your g of 2. 4 minus 8 is negative 4. Box your answer. So we're taking the number inside of the parentheses and we're substituting it in for x. That's all we're doing. So on number 16, f of negative 5, so that means I'm going to use this guy right here. So I'm going to bring down this f of x equals 2x minus 4. That's going to help me. Everywhere I have an x, I'm going to put parentheses around it. and I can substitute in. So f of negative 5 equals 2 times negative 5 minus 4. Now, I can simplify this part over here. So I'm going to bring down my f of negative 5 equals 2 times negative 5 is negative 10. Bring down my minus 4. F of negative 5 equals negative 10 minus negative 4 is negative 14. Box your answers. Number 17, g of negative 3. Now, g means we're going to be using this guy right here. So I'm going to rewrite the equation. G of x equals x squared minus 4x. And then I'm going to go back through and put parentheses everywhere I see the x. Not around what's attached to it, just the variable. Now I can substitute in negative 3. Negative 3 goes in everywhere I see the x. So g of negative 3 equals negative 3 in parentheses, very important, squared, move this over a little bit, minus 4 parentheses negative 3. Now, if you're choosing to put this in your calculator, you need to make sure you put the parentheses around it as well. If you don't, you're not going to get the same answer. So, if I take negative 3 and square it, that's going to give me negative 3 times negative 3, which is a positive 9. If you put it into your calculator like this, negative 3 squared, your calculator reads that as the opposite of 3 squared. Now, you got to be smarter than your calculator because you know that negative 3 squared is really a positive 9, and now it's giving us a negative 9. So you need to put parentheses around that negative 3 before you square it, and it'll get you the positive 9. Then I have minus a 4 times a negative 3. So that's like a negative 4 times a negative 3, which is a positive 12. And then we can add those together. And g of negative 3 equals 21. And box your answer. All right, if you have any questions on those, please make sure you come see me.